In this video, we're going to be going over the polar form of complex numbers and DeMoivre's theorem. To begin with, we're going to start with going over the absolute value of a complex number. So if you recall, the definition of absolute value is the distance away from zero that a number is. So if our number is a complex number, the absolute value of that complex number is just going to be the distance that that number is away from zero. Now, if you recall, when we went over complex numbers, we saw that we could plot them on a two-dimensional graph. So if we have this complex number, 3 plus 2i, we said that the horizontal axis was the real number line and the vertical axis was the horizontal number line. So the point 3 plus 2i we could plot right here. Now the origin is at the 0 plus 0i, and the distance from the origin, we're going to call that distance the absolute value of the complex number. So how we would write this, we would say that z, and z is just signifying a complex number, so our given complex number z is 3 plus 2i. What we want to do is we want to know the distance that z is away from the origin. So we're going to say the absolute value of z. And what is that distance? Well, this right here, the vertical is 2, the horizontal is 3, so to find that distance we're just going to use the Pythagorean theorem. So 2 squared plus 3 squared, and then take the square root of that. So the absolute value of the number z is going to be the square root of 13. In general, if we want to find the absolute value of a complex number, z, what we're going to do is we're going to say a squared plus b squared, and whatever the square root is, where z is equal to a plus bi. Okay, so if we have a complex number z, and it's written as a plus bi, to find the absolute value of z, we take the a value and the b value. We do not include, or notice here how it's just the b value. It's not bi that's getting squared. Now we want to be able to write the polar form of a complex number. Typically when we have written complex numbers before, we wrote them in the form a plus bi. We're going to call this rectangular form. Now what we want to be able to do is write this in polar form, and when we saw this written in rectangular form, we could write this or plot this point on the complex plane where we had real numbers along the real part of the complex number along the horizontal axis and the imaginary number or part along the vertical axis. Now what we want to do is we want to write this in polar form. So as a reminder, to plot a point in polar form, we need the r value and the theta value. So r is just the distance from 0, and theta is the angle. So here these are, or if a point is written in r comma theta form, we call this polar coordinates. Remember where r can be found with a squared plus b squared square rooted, with a equal to r cos theta, b equal to r sine theta. So putting this all together to write the polar form of a complex number, a plus bi, what we do is we say this is r times cosine theta plus I sine theta. So if we're given, again, a complex number in rectangular form, a plus bi, to write this in polar form, we need the r value, which is just the distance from 0, and then we need the angle theta, and we take cosine of that angle theta plus I sine of that angle theta. So this first example has a complex number z equals 2 times cosine pi over theta plus I sine pi over theta. This is in polar form. What we want to do is write this in rectangular form. So to write this in rectangular form, it's pretty straightforward. We take the complex number, cosine pi over 6 plus I sine pi over 6. So what we see here is that 2 is the r value, and then pi over 6 is the theta value. So to find this, or to convert this into rectangular form, all we need to do is simplify and multiply this out. So cosine at pi over 6, that is square root 3 over 2, plus I times sine at pi over 6 is 1/2. And then we just distribute the 2. So 2 times root 3 over 2, that's just going to be square root of 3, plus 2 times 1/2 is just 1, so plus I. So that would be the complex number written in rectangular form. And what we can see is that the A value is square root of 3, the B value is 1. The B value is the coefficient on the imaginary part. Now we're going to go the other direction. We have a complex number z equal to square root of 3 minus I. We want to write that in polar form. So again, polar form of that complex number z is going to be r times cosine theta plus I sine theta. So what we need to do is we need to figure out the r value, and we need to figure out theta here. So the r value is just the distance that this point is away from 0. So square root of 3 is the horizontal or the real portion, and then negative I, so negative 1I, square root 3. So this point is down here. Okay, so this is going to be negative 1. So what we need to do is find r. We're going to use the Pythagorean theorem here. So r squared is equal to square root of 3 squared plus negative 1 squared. We get r squared is equal to 3 plus 1. So r is going to be positive 2. And then we need to figure out what this angle theta is. So this angle, we're just going to use tangent of theta is equal to negative 1 over square root 3. And if I rationalize that by multiplying the top and bottom by square root 3, we get tangent of theta is equal to negative square root 3 over 3. So what angle is that? The angle is 330 degrees, or 11 pi over 6. Okay, this question does not mention whether we want to be in radians or degrees, so either of these angles for theta are appropriate. So putting this all together, we're going to say z is equal to 2 times cosine, I'm going to use degrees, 330 degrees, plus I sine 330 degrees, and there we have it. Alternatively, we could have said z is equal to 2 cosine, we could use radians, so 11 pi over 6 plus I sine 11 pi over 6. That is also an appropriate conversion into polar form. We could keep going actually, because 330 degrees, we could write that as any coterminal angle in degrees. So we could say negative 30, we could say negative 390, we could say 690 degrees, and so on. We could just keep changing these or converting these into a different coterminal angle. And you could do the same thing for the angle measured in radians. Typically though, we write our angle with between 0 and 360, or between 0 and 2 pi. So in the first revolution around the circle. Next we'll move to multiplying and dividing complex numbers. So the first question to look at is, how do we multiply two complex numbers that are written in rectangular form? Well, we've already seen how to do this previously. What we do is, these are two complex numbers that are, binomial in form. So what we're going to do is we can distribute or FOIL here, and then we'll simplify and combine the like terms. So 1 times 4 root 3, we have 4 square root 3. 1 times 4i is plus 4i. I root 3 times 4 root 3, we get plus 4i square root of 9, and then plus 4i squared square root of 3. Then we can do some simplification. 4 square root of 3, we have 4i plus 4i root 9. Well, root 9 is 3, so we're going to get 4i plus 4i times 3 is 12i, and then I squared is negative 1. This is negative 1 times 4 is negative 4 square root 3, and then we can continue to combine 4 root 3 and negative 4 root 3 is 0, 4i and 12i is 16i. Okay, so that is a refresher on how we multiply two complex numbers when we have them written in rectangular form. However, what's going to happen if these numbers are written in complex form? Or rather, sorry, they are complex numbers. What's going to happen when we write them into polar form? How do we multiply those? Well, what we can do is, if we are given the complex numbers in polar form, there's a product rule that we can follow. So if we have two complex numbers, z1 and z2, and we're multiplying those, what we do is we multiply the r values, so r1 times r2, and then what we're going to do is we're going to add the angles, so theta 1 plus theta 2 plus I sine theta 1 plus theta 2. Okay, so in this previous question, we're given the numbers in rectangular form. If we're given the numbers in polar form, we can follow this algorithm. So these two numbers up here, if we were to convert those into polar form, I'm not going to show how to do that, but I'll leave that to you. This is what we get for z1 and z2 if we were to convert what we had up here. Each of those complex numbers were in from rectangular form and now writing them in polar form. Now if we want to multiply those, we're just going to follow this algorithm. So what we do, z1 times z2, so I'm going to multiply r1 and r2, so the r's are 2 and 8, so 2 times 8 is 16. Then we're going to multiply that by cosine of, well, now I add the angles together, so 60 plus 30 is 90 degrees, plus I sine, I'm always going to get the same angle for each of the arguments here. Simplifying this, I get 16 cosine of 90, well that's 0, plus I sine of 90 is 1. So what we get is 16 times 0 plus 16 times I, we get 16i. And that, confirms with what we had up here. So depending on how the number is given to us, whether we're in rectangular form or polar form, that will determine how we want to multiply. There's a similar algorithm when we want to divide complex numbers. First, if we are in rectangular form, I don't have an example written down, but if we have something like this, 2 plus 3i divided by 5 minus I, how we write this is we write it as a fraction, and if you recall, we multiply the top and bottom by the conjugate, and then we're able to simplify. So I'll just put dot 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 after that. So if that's what we would do if we're in rectangular form. If we're in polar form, we're going to use a similar idea to what we saw back here. Remember, back here we multiplied the r values and we added the angles. Now what we're going to do is, if I have z1 divided by z2, what we do is we divide the r values and we subtract the angles. Too many parentheses. So we'll say theta 1 minus theta 2 plus I sine theta 1 minus theta 2. So that will be our algorithm when we are trying to divide complex numbers in polar form. Alright, here we are given two complex numbers written in polar form, z1 and z2. We want to find z1 times z2 and z1 divided by z2. So z1 times z2, remember what we do is we multiply the r value, so 3 times 4 is 12, and then we're going to say cosine of 65 plus 15 plus I sine 65 plus 15. We get 12 times cosine 65 plus 15 is 80 degrees plus I sine of 80 degrees. Now, this is as far as we can go if we don't have a calculator, and the reason is 80 is not a known value from the unit circle. So this is as good as we can do here. If we had a calculator, we could certainly punch in cosine of 80 and sine of 80 and simplify this a little further. But for right now, that's good enough. And then dividing, well, what we do is we divide the r values, so we'll have 3/4. Now we subtract the angles, so cosine, we'll have 65 minus 15 is 50 degrees, plus I sine 50 degrees. And again, because we don't have a calculator, this is as far as we're going to go. Moving on from basic multiplication and division, let's see how we can perform a few other computations when we have complex numbers. The first of which is, how do we compute something like 3 plus 6i raised to the 4th power? Well, if something's raised to the 4th power, that just means it's getting multiplied by itself 4 times. So conceivably, we could carry out this multiplication. While this would not be very difficult, probably pretty tedious, and this is only when we're raised to the 4th. What happens if we're raised to the 12th power? We're going to write this, or we would need to write these binomials 12 times, and that's not that's not ideal. So what we want to do first is convert to polar form, because polar form makes raising complex numbers to exponents a lot simpler. So simplifies, let's say exponentiation of complex numbers. So we'll convert to polar form first, and then what we can do is we use something called DeMoivre's theorem. And what DeMoivre's theorem says is, if we have a complex number z raised to some power n, how we calculate that is we say we raise r to the n value. Actually, let me clean that up a little. Z raised to the nth power. How we calculate that is we raise r to that same n power. Then we say cosine of n times theta plus I sine of n times theta. Okay, so basically what we're doing is whatever exponent we have, n, we raise the r value from the polar form of the complex number. We raise r to that same exponent. Then what we do is we multiply the argument, the angle of sine and cosine, times whatever the value of n is. So this is called DeMoivre's theorem here. So let's check this out in practice. Okay, so this example gives a complex number z of 1 plus I, and it says to use DeMoivre's theorem to find z to the 16th and z to the negative 6th. And then let's write our answers in rectangular form. And remember, rectangular form, that's just a plus bi form. Okay, so the first thing we are going to need to do, let's do z to the 16th first. So z raised to the 16th. And again, what this means is we want to find this, 1 plus I raised to the 16th. So again, instead of writing 1 plus I as a factor 16 times and multiplying it out, what we're going to do is we're going to convert this first into polar form. So the polar form, we need to know what the r value is, and we need to know theta. So I'm going to just graph this point. We're going to have 1 plus I right here. We need to figure out what the r value is. Well, the horizontal value is 1, the vertical value is 1, so r squared equals 1 squared plus 1 squared. R squared equals 2, so r is going to be square root of 2. And then theta down here, well, we want tangent of theta is equal to 1 over 1. So where is tangent? What angle has a tangent value of 1? And that's going to be at 45 degrees. So we'll say theta is equal to 45 degrees. So we have the r value, we have theta. So this complex number in polar form is going to be square root of 2 times cosine 45 degrees plus I sine 45 degrees. All right, now what we want to do is raise that to the 16th power. So we're going to say z to the 16th is equal to, well, we take the r value, raise that to the 16th, and then we say cosine of 16 times 45 degrees plus I sine 16 times 45 degrees. And close that. All right, well, square root of 2 is the same as 2 to the 1/2. So 2 to the 1/2 raised to the 16th, we're going to get 2 to the 8th power. And what we end up with, 16 times 45, that's the same as 8 times 90, so that's 720. So cosine 720 degrees plus I sine 720 degrees. Cosine at 720, well, 720 is just 2 times around the unit circle, so that's the same thing actually as cosine of 0 degrees plus I sine 0 degrees. And simplifying this further, 2 to the 8th is 256. Cosine at 0, well, that's 1. Plus sine at 0, that's 0, so we get 0 times I, so that's just 0. And so what we end up with is 256 times 1 is 256, and then 256 times 0i is just 0. So this is what we would end up with, 256. So this process, much easier than writing out 1 plus I 16 times and multiplying that. Now, we also want to figure out z raised to the negative 6th, so let's do that on this next slide. Alright, so we want to find z raised to the negative 6th. I rewrote our complex number in polar form here. So this will be z to the negative 6th is equal to, well, square root of 2 is 2 to the 1/2. We're going to raise that to the negative 6th, and then cosine of 45 times negative 6 plus I sine 45 times negative 6. And what we'll have here is 2 to the negative 3 times 45 times 6, well, I could do 90 times 3, so negative 270, cosine of negative 270 plus I sine negative 270. 2 to the negative 3, that's the same thing as 1 over 2 to the 3rd, so 1 over 2 to the 3rd. Cosine of negative 270, well, negative 270, negative 270 is going to be up here, so that's going to be 0 for cosine, so that would be 0 plus, sine has a value of 1 there, so 1i, or just I, we get 1/8 times 0 plus I, we get 1 over 8i, and that's it. So z to the negative 6th is 1 over 8 times I. And this is in fact in rectangular form. If we wanted to write this explicitly, where the a value is 0, we could write it like that. So now it's in a plus bi form, where a is 0 and b is 1/8. But this form is perfectly appropriate. So we'll move on to finding the roots of complex numbers, and this is kind of part 2 of DeMoivre's theorem. And so DeMoivre's nth roots theorem says that the nth roots of a complex number, if this is our complex number in polar form, where r is greater than 0, so r is positive and theta is in degrees, the roots are given by this expression. You can read that r to the 1 over n and then times cosine plus I sine. And so the argument here, what we're going to do is we use different values of k. So we start at 0 always, and then we go up to 1 less than whatever root we're finding. So if we're finding the 10th roots, we're going to go from 0 to 9 for the k values. Now, when we're finding roots of a number, whatever root we're finding, that's how many roots there are. So if there's, if we're finding the square roots, there's always going to be 2. If we're finding the cube roots, there's going to be 3 of them. If we're finding the 4th roots, there's going to be 4 of them, and so on. So a couple of examples of using DeMoivre's roots theorem. Let's find the 3 cube roots of -1 plus I. Let's do that in polar form with the argument in degrees. So the first thing we need to do is write our complex number in polar form. So -1, 1, so that complex number is here, -1 plus I. So we need to find the r value, but the vertical value is 1 because it's 1i, and then -1 along the horizontal axis. So r here will be -1 squared plus 1 squared, so r squared is equal to 2. R is going to be 2. Then we need to figure out what that angle theta is. Well, tangent theta is equal to opposite over adjacent. So tangent theta is equal to -1. Tangent in the second quadrant is equal to -1 at 135 degrees. So theta is equal to 135 degrees. So this complex number z in polar form is going to be 2 times cosine 135 degrees plus I sine 135 degrees. Alright, so we've converted this number into polar form. Now we need to find the 3 cube roots. So what we do is we start at k equal to 0, and we're going to say the first complex number will be, or the first root will be, this should be, I made a mistake over here. The r value is square root of 2. Square root of 2. So k equal to 0, we're going to have square root of 2 raised to the 1/3 power times cosine of, so we start with our angle theta plus 360 times k, and our k value here is 0. And we divide that by whatever the n value is, which is 3, plus I sine times 135 plus 360 times 0 divided by 3. And then we simplify this. Well, square root of 2, we can write that with an exponent of 2 to the 1/2. So this is 2 to the 1/2 raised to the 1/3. And then we're going to have cosine. Well, 360 times 0 is just 0, so this is going to be 135 over 3 plus I sine of 135 over 3. And then 2 to the 1/2 all raised to the 1/3, that's going to be 2 to the 1/6 power. And then cosine 135 divided by 3 is 45, so cosine of 45 plus I sine 45 degrees. And that's it. So this is polar form. And the question says to just leave the answer in polar form. So this is one of the cube roots, if we leave that in polar form. Now, if we wanted to convert this, or to continue and write this in rectangular form, what we would do is we'd say 2 to the 1/6 times, well, cosine at 45 is root 2 over 2 plus I times root 2 over 2, or root 2 over 2i. Okay, and then we would multiply that out. Well, this is when things are going to get a little hairy because these square root 2's are 2 to the 1/2, and this is over 1. So 2 to the 1/6 times 2 to the 1/2 is going to be, well, we need to add the exponents, so that's 3/6 So 2 to the 4/6 over 2 plus 2 to the 4/6 over 2i, and 4/6 is 2/3. So this will be 2 to the 2/3 over 2 plus 2 to the 2/3 over 2i, and we could go a little further. And if we do that, let's see, I'm kind of running out of room here. Well, let me pick a different color. 2 to the 2/3, if I divide that by 2, well, when we're dividing and the bases are the same, we can subtract the exponents. The exponent right now in the denominator is a 1, but getting a common denominator, that's going to be 3 over 3. So that's going to be 2 to the negative 1/3, which is 1 over 2 to the 3rd. So I could rewrite this finally as 1 over 2 to the 3rd is 8 plus 1 over 8i. So that would be the most simplified that we could get if we wanted to write this in rectangular form. But the question just says keep this in polar form, and we can see that converting this into rectangular form is a little bit more tedious work. So polar form is a great option here. Okay, so we found the first cube root, and that occurs when k is equal to 0. We need to also find the other two cube roots. Remember, since we're looking for cube roots, there are going to be 3 of them. So we need to evaluate when k is equal to 1 and when k is equal to 2. So k equal to 1, what we'll say is that square root of 2 raised to the 1/6, rather 1/3, cosine of 135 plus 360 times 1, because k is 1, divided by n, which is 3, plus I sine 135 plus 360 times 1 divided by 3. So this is just, again, an exercise in simplification. Square root of 2 to the 1/3, we already saw that that's going to be 2 to the 1/6. Cosine of, well, 135 plus 360, that's going to be 495. 495 divided by 3 is 165. So it's 165 degrees plus I sine 165 degrees. And that's it. We want to leave this in polar form. So 2 to the 1/6 times cosine 165 degrees plus I sine 165 degrees. Alright, and then when k is equal to 2, we follow the same procedure. Square root of 2 raised to the 1/3 times cosine of 135 plus 360 times 2 divided by 3 plus I sine 135 plus 360 times 2 divided by 3. And we're multiplying by 2 here and here because k is equal to 2. And then simplifying, we're going to have 2 to the 1/6 times cosine of, well, 360 times 2 is 720, plus 135 is 855. 855 divided by 3 gets us 285 degrees, plus I sine 285 degrees. And that's it. So when k is 2, we have 2 to the 1/6 times cosine of 285 plus I sine 285. And that's it. So these are the 3 cube roots, of our complex number. Now, we could check these if we wanted to by raising any of these numbers to the 3rd power oops, I'm hitting the next page button. So if we wanted to raise this to the third power, all we need to do is, well, we multiply the exponent here times 3, so that'll be 1/2, which is square root of 2, which is this. And then what we do is we take the argument and we multiply it by 3. So we're going to get 135, 135, so we're good. If we were to do that for k is equal to 1, if we raise that to the third power, again, we would get 2, or square root of 2. And then 165 times 3 is 495. So 165 times 3 is 495. But that's coterminal with 135. So that's, again, how we're going to get that 135 degrees. And the same thing would happen when k is equal to 2. If we raise that to the third power, we're going to get back to where we started. So this is a way to see kind of what we're doing here. We're undoing the exponent when we take a root. So to redo that root, we raise it to that given exponent. Okay, and one last example. Let's find the 3 cube roots of 64. And same thing, let's use, actually, let's use rectangular form. For the answers, or for the roots, I guess. This is slightly different than the question that is in the notes. I wanted to change it up, and I wanted to go through an example where we give the solution in rectangular form. All right. However, we still need to convert this number 64. We need to convert that to polar form. Now, it may not look like this is a complex number, but we can write 64 as in a plus bi form. That's going to be 64 plus 0i, right? So 64, if we were to graph that, would just be 64 along the horizontal axis. So if we wanted to write this in r cosine theta plus I sine theta form, well, the r value, well, the distance from the origin is 64, so r is going to be 64. And then what is that angle there? Well, that angle is 0. 0 degrees or 0 radians. So we could say cosine of 0 plus I sine of 0. So writing this in polar form, well, we're just going to have cosine of 0 is 1, so this would be 64 times 1 plus 0i, so that's just 64. So 64 here, and the 64 that we just calculated, it's unclear whether we want to think about this as being in polar form or rectangular form. However, because we're finding the cube roots, and to use DeMoivre's theorem, we want to think of this as being in polar form. Even though 64, we can think of that as being in either rectangular or polar form. So since there's 3 roots here, we're going to look at k equals 0, k equal 1, and k is equal to 2. So 64 raised to the 1/3 times cosine of 0 degrees plus 360 degrees divided by, or 360 times 0, because k is 0. And then we're going to divide that by 3, which is the n value. The n is just how many, or what root are we taking, plus I sine 0 degrees plus 360 times 0 divided by 3. So what we end up with is 64 to the 1/3. Well, what's the cube root of 64? Well, if we're only dealing in real numbers, that's just going to be 4. And then we'll have cosine of, we have 0 plus 360 times 0 divided by 3, so that's just 0 divided by 3, which is 0, plus I sine also 0. 4 times cosine of 0 is 1, plus I sine of 0, that's just 0i, so that's 4. So 4 is our first cube root. And when we're dealing in just the real numbers, we know that 4 is the cube root. 4 raised to the 3rd power is 64. So that makes perfect sense. Now when we look at k equal to 1 and k equal 2, we're going to see some values that are not real numbers. So 64 to the 1/3 times cosine of 0 degrees plus 360 times 1, and again 1 because k is equal to 1, divided by 3 plus I sine 0 degrees plus 360 times 1 divided by 3. 64 to the 1/3, that is 4. Cosine of, that's going to be 360 over 3, which is 120, so cosine of 120 degrees plus I sine 120 degrees. Well, what is cosine at 120 degrees? That's going to be, what, negative 1/2. And what is sine at 120 degrees? That's root 3 over 2, so root 3 over 2i. Then multiplying that out, we're going to have negative 2 plus 2 square root 3i. So that is our second root. And then we need to calculate k equal to 2 here. This will be 64 raised to the 1/3 times cosine of 0 plus 360 times 3, or I'm sorry, 2, because k is equal to 2. Divide that by 3 plus I sine 0 plus 360 times 2 divided by 3. So again, 64, the cube root of 64, that's going to be 4. Cosine, well, we have 360 times 2 is 720. 720 divided by 3, we get 240. So cosine 240 degrees plus I sine 240 degrees. So we'll have 4. Cosine at 240, that's going to be negative 1/2. Sine at 240 is negative root 3 over 2. So what we end up with is negative 2 minus root 3 over 2i. And what you'll notice is when k is equal to 2, we get negative 2 minus root 3 over 2i. When k is equal to 1, we get the conjugate, negative 2 plus 2 root 3 times i. And that makes sense because if you recall, when we were talking about zeros of radicals, anytime we take a square root, we always get conjugate pairs. It's a similar idea here. When we're taking roots, we should get, if we have roots that are, if we have roots that are irrational or complex numbers, they're always going to show up in conjugate pairs. So when k is equal to 1 and when k is equal to 2, these values right here are conjugates of each other. So that's a good thing. That would be something to check as we're going through a problem like this.